I would like to welcome everyone to this third in the series of 3 Van Horn Distinguished Lectures by Professor Harry Atwater of Caltech. And we are happy to be back in what Ernie Banks, Hall of Fame first baseman for the Chicago Cubs, would call the friendly confines, in this case of White 411, our department's auditorium. I have a few observations after the first 2 lectures in this series. First of all, we've been fortunate to receive lectures from an extremely productive researcher. And what also struck me was how all 3 of these lectures have emanated from a single innate, passionate fascination with the interaction of light with materials, and how Professor Atwater has been able to convert that into a very influential career. He's widely cited, and clearly he has had many outstanding ideas that have been picked up on, that he's implemented and that others have pursued as well. His talks have been excellent. He has put his topics in a historical context, which I think is ideal for a series like this. He's grounded his talks in fundamentals that are familiar to all of us here. Plus, he's been able to provide new insights into some of those fundamentals. Like, we may have forgotten that photons have entropy associated with them. And the theme of today's talk will rely on the fact that photons, without mass, still have momentum. So that's an exciting concept. And in addition, there have been plenty of cutting-edge topics covered in his talks for those who are expert in this field. Another thing that is inescapable is, as influential as Professor Atwater's own work has been, he has also been quick to acknowledge breakthrough achievements by other researchers in his field. And what that tells me is that when you have ambitious goals that you're striving towards, you sense a shared purpose with the community at large, your fellow scientists working in related fields and even fields unrelated to what you're doing. That it takes many individuals and many accomplishments to achieve ambitious goals. And so my last comment is directed really at all of us, but in particular to the younger researchers in the field. Harry Atwater and I did our PhD work at MIT in the same building at the same time. We overlapped for a couple of years. I worked on the 5th floor, he worked on the 3rd floor, and maybe that's my excuse, but I never really took the opportunity to get to know Harry Atwater, and I consider that a missed opportunity. It's an opportunity that I hope to make up for by becoming more acquainted with his work now. But I think that should be a reminder to all of us to look at the people who are sitting in the room with us. And maybe they do work 2 floors away from you, which might seem like an insurmountable barrier at this time. But make the effort to get to know what your colleagues are doing, because you have no way of knowing on April 19th, 2018, which of these colleagues will cross paths with you again, and with which of these colleagues you will be able to renew your own shared sense of purpose. So, with that, let's welcome the 3rd lecture. Professor Atwater, the floor is yours.
Thank you, Mark, and I want to say also thank you to the faculty, the grad students, and the undergrads. It's been a very enjoyable week, very productive, and I've learned many things about Case Western this week. I've learned you have a faculty that is bringing to the School of Engineering and to the campus a very vibrant research program that actually has many ties to industry, which is really exciting to see. I see that as a sign of real health. And I see a faculty that's very, very collegial and genuinely seems to like one another, which is great. That ends up reflecting indirectly and being great for the students as well. And then finally, I'll say that through the lunches and dinners we've had, I found out that Cleveland has fantastic places to eat. And I want to say thank you for that. And my view of Cleveland is to transform it as part of the cosmopolitan universe. So I wanted to start today, and this is going to, I'm going to beg your indulgence to go in a direction that's very unorthodox. And in the spirit, for those of you who are from the metallurgy side, think about this in the spirit of Michael Ashby's material selection kind of initiative. So what we're going to do is kind of a material selection analysis on what are the characteristics of materials that we would ask for interstellar travel. And this is a sort of mind-blowing concept and literally out of this world, and we're going to carry forward and take a look at that today. This little thing right here is an artist rendition of what such a spacecraft would look like, and this, by the way, is not the Earth. It is a planet around another nearby star. So the concept here is to develop the engineering principles that I think are almost within reach to develop spacecraft that will allow us to travel within our lifetimes to nearby stars. Okay, the work itself, once again, is only made possible and completely the people who are completely responsible for the advances are this outstanding group of young people, students and postdocs and research scientists who are passionately engaged in it. So I want to start with a notion. Each of us is in some measure a scientist and also an engineer. And one of our Caltech heroes opined once that scientists discover the world that exists and engineers create the world that never was. So what we're going to try to do today is think a little bit about that world that never was and don our engineering caps and try to engage this problem. So let's think about this problem, and we're going to think about it in terms of characteristic performance and complexity, where our figure of merit is going to be the power per unit weight. And if we go from historical examples of power per unit weight in the pre-machine age, pre-internal combustion machine age, we can actually track and sort of track the progress in terms of increase in power per unit weight in watts per kilogram. And what you'll see here as we go from to the automotive age, from the horse and buggy age, we get into the range of tens of watts per kilogram with an efficient car. With an inefficient racing car, we can get up to about a kilowatt per kilogram. Here, with a NASA space plane and a Boeing 747, we're in the range of 1 to 10 kilowatts per kilogram. Here, when we go to the space shuttle or the SpaceX Falcon Heavy rocket, we're now getting into the range of 10 to 100 kilowatts per kilogram. And up here is a special spacecraft. This is a Dawn spacecraft. It actually has a historical connection to the Cleveland area because it is a spacecraft that is driven by solar electric propulsion driven by an ion engine. And the ion engine was actually invented by a guy named Harold Kaufman, who worked at what was then NASA Lewis Research Center, now NASA Glenn Research Center, and allows us a method of propulsion that allows us to get up here to the very high power densities. And in fact, we'll see importantly also the mass and the terminal velocity of the propellant will actually define the final speed that we can get to for spacecraft. And importantly, this is a spacecraft that, because it has an ion thruster, is capable of not only doing flybys of remote celestial bodies, but it actually can use its thrust to brake and insert into orbits as well. So the question is, what lies up here? What lies up in this megawatt per kilogram or higher level? So this is one of the things we're going to talk about today. And so this is a problem where inevitably at every step along the way, you already know that materials play an incredibly decisive role in determining whether or not we can make these advances. So let's think a little bit about the strategy that we're going to adopt. The strategy for these kinds of machines that we already know about is one where conceptually the paradigm is that the power and the propellant are both on board the vehicle. okay? So we carry our fuel with us, and that gives us range. We can fly around the world, but that fuel to weight ratio then limits the cruise speed and ultimately limits the range. The special thing about the spacecraft that I showed you, the Dawn spacecraft, born here in Cleveland, at least the ion engine part, is that it separates, it breaks this conceptual paradigm a little bit in the sense that the power is external, even though the propellant is on board, okay? So the power is solar power. The solar power produces DC electricity. The DC electricity is used to drive the ion engine. The propellant in the ion engine is a gas, or in some cases molecules like C60. And this results in an increase in power per unit mass. The ultimate, of course, is where the power and the propellant are both external to the spacecraft. And we're going to explore that as well. Okay, so the outline of my talk, I'm going to begin first talking about ultralight systems that are maybe a little closer to this world in the sense that they're things that will be useful to us in the coming era of commercial and government-led space exploration, which are ultralight power systems based on very lightweight photovoltaics. I'll say a little bit about what some of the options are there. And then I'm going to talk about laser-driven spacecraft propulsion that will allow us to potentially go to the stars. So let's think about where we are with regard to solar power. So in the 1990s to 2000, we developed a technology that allowed us to develop the International Space Station and many commercial communications and navigation satellites. And then in the 2000 to 2010 range, we started to see spacecraft like the Dawn and the SMART spacecraft that have solar electric propulsion, and it's an advance. There's another type of very interesting spacecraft we'll talk about called a solar sail that uses radiation pressure, photon momentum pressure coming from the sun as the propellant. Very low impulse, but it allows, it's something where there are now these types of spacecraft are coming to reality. You have to be patient, of course, with this kind of spacecraft. And so what people are thinking about now are spacecraft where this concept of marrying solar electric propulsion with solar power would allow us to really build sort of workhorse spacecraft in space, where we could actually manipulate things, not only the spacecraft's orbit, but perhaps payloads. Also, we can develop large-scale platforms for power generation in space. And that has some very interesting implications that I'll talk about in a minute. We've started an initiative, a space solar power initiative at Caltech that I'll share some initial results with you about. And that the ability to bring large amounts of power to lightweight structures in space has many kinds of implications for the way we actually look at our world and the way we communicate. The ability to bring forward systems for global monitoring and communications via global internet, which is actually starting to become a very big commercial. There's a big commercial impetus for this right now. So this is the kind of conceptual driver for the project that we've started at Caltech. The notion that by taking a modular design where we build a little unit element tile that's 100 square centimeters in diameter, or in size, is square tile, actually rectangular. This structure generates solar power on one side by photovoltaic energy conversion, uses an integrated circuit to convert the solar DC power to microwave energy, and uses that microwave energy to drive a set of antennas that is on the other side of the tile. And then by arranging these tiles in a dense array, we can create a phased array. In my lecture yesterday, I talked about phased array radars. And this same phased array concept can be used for power beaming. It's already been demonstrated by NASA more than 15 years ago. And with a large aperture, we can beam power from long distances quite precisely. Now, this is, of course, a completely fictitious artist's view, but the concept here is that by starting with this unit element that is mass manufacturable and modular, where there is no central element, this could easily be flexibly expanded from the single cell to the module to a large system level. And different systems will have different power requirements. And the concept for the power for a stationary power generation would be to launch this into geostationary orbit. Smaller systems could be located in low Earth orbit to be used for remote mission power, beaming power to places where there is no utility network, for example, where you need continuous large amounts of power day and night. Electric powered aviation, beaming power actually down to remote electric powered fleets of airplanes that fly 24 hours a day. This is something that has also attracted some attention. Global internet, and another concept called bistatic radar, where you locate the radar that's used for imaging and range finding not on the Earth, but remotely in space, and it communicates with images and range finds objects in the sky, but then which are then detected on the Earth. So there are a range of technologies that can take advantage of ultralight power systems in space, combined with the ability to beam power wirelessly. So the concept that we have is a modular concept where we start with a single tile and build these tiles into strips. I don't have time to tell you about this all today, but this is something that within the context of our Space Solar Power Initiative, working together with my colleagues Sergio Pellegrino and Ali Hajimiri at Caltech. Sergio is an aeronautical engineer that specializes in the construction and deployment of large-scale space power systems, or space systems, to build things that are deployable. And this structure, for example, 60 meters by 60 meters, is about the same size as the solar sail that I showed you on one of the previous slides. And then these can be assembled in formation flying arrays of spacecraft at whatever scale the application demands. And so just to give you, particularly for the students to think about this, what is the concept, or what are the implications of having a space-based power system? This is something, by the way, that has been a sort of twinkle in the eye. It's been sort of an imaginative idea, always out of reach, ever since the beginning of the space program. And in fact, I think even before that, people like Asimov even imagined this kind of concept, where large power generation in space could generate power that could be beamed wirelessly to the Earth. So let's just do sort of an energy analysis on this. First of all, in space, there's about 30% higher power density than there is on the Earth because of the absence of the atmosphere. There's more light overall and more in the blue and ultraviolet. With a ground station consisting of an array of rectennas, that is basically devices that convert microwave energy to DC. These are all very straightforward and already exist. They can be made very inexpensively. We can then think about beaming power 24 hours a day, 7 days a week. And so then if we think about the implications of this, compared to the predictably intermittent solar power on the surface of the Earth, we get 9 times more power. So, and it's continuous. So this actually is a scheme for a geostationary or median Earth orbit basing would not require storage except in very intermittent conditions. So this is of course a long way off and may be difficult to realize, but at least it gives you an idea to think about how you could deploy these systems and what the merits might be. And in fact, we've done economic analyses of how inexpensive this would need to be and how lightweight, how low the launch costs would have to be to rival the cost of terrestrial solar power. And we're not orders of magnitude off in our current kind of engineering approach to how you would do this. So here's, for example, how the conversion efficiency would look. Suppose you start with sunlight in space and you have losses due to the concentration of sunlight, the conversion, the DC to RF conversion, the RF transmission and downlink, and then the conversion of RF to DC, and then the conversion of DC to AC power grid. And so of the power that's available in space 24 hours a day, you could ultimately bring into the AC power network on the ground somewhere between 5 and 19% of that power. So that's quite an interesting concept. So I want to start here and mention that we have actually built the very first, I'm going to stop here for a minute and show you that we have built and realized the unit element, which is the tile. And this is an initiative that we've taken over the last couple of years. And this is the tile. Let's see if I can make this. There we go. So this is a tile that's sitting under a solar simulator. It has trough concentrator photovoltaic elements. I'll describe these in a minute. And on the bottom here is, in the middle you'll see in a minute, there's a RF CMOS integrated circuit designed by my colleague Ali Hajimiri that converts DC power to 10 gigahertz microwave energy. And then there's an array of thin film microwave patch antennas that are in this plane here. The DC power is generated here, converted to RF, and then fed to these antennas. And you'll see that we can actually, under the solar simulator, down here, let me see if I can get this out of the way. This is a rectenna array that's being held by one of the students here, and you can see this little LED that's being lit right here. That's microwave energy that's being beamed from these solar cells, these thin strip solar cells located on the concentrators, being fed. There's the integrated circuit chip. Here is the RF antenna array, and then this is sitting on just a fiber board structure, and it's beaming power down to this little LED that's attached to the rectenna. So the power is being, it's a little bit hard to see because this thing is in the way, but there's the LED being lit up by the rectenna. So this is showing the unit element of this structure, this solar tile in operation. Okay, so let's say a little bit about generating power in space and what some of the issues are. I talked in my first lecture on Tuesday about power generation using efficient power generation materials like gallium arsenide. And so let's talk a little bit about the weather in space and the space environment. Here in Cleveland we have cloudy weather. It's a little cool. Sometimes it rains. In space we have much more severe weather. We have high energy particle radiation. We have a high UV content. We have a very extreme thermal cycling. We have vacuum. That is good in most respects. If you're close to the Earth, you also have atomic oxygen, which is very reactive. You can also see, depending on where you are, if you're outside the Van Allen belts that are basically serve to shield the Earth from these high energy particles that produce magnetic fields that shield the Earth. Then we have exposure to the full flux of these particles. And so most spacecraft of the ones that I showed you on my opening slides are powered by 3,5 compound solar cells of the kind I talked about on Tuesday using gallium arsenide and gallium phosphide. They're multi-junction cells for high efficiency. But they require something to insulate them from this weather, sort of an umbrella to prevent the interaction with the weather. Here's the problem. With something like a gallium arsenide solar cell, if we start at the beginning of life with some power, some output efficiency at the beginning of life, depending on the flux of protons between 100 kilovolts and 10 megavolts, I could lose more than half of the power generation over the lifetime of the and this is a real problem. And likewise, with high energy electrons that are part of the solar wind as well, which are of the order of a megavolt, there's a whole energy distribution from a little less than a megavolt to a few megavolts. We can also lose half the power. So therefore, we need, these materials are very radiation sensitive, and we need to put shielding on top of our solar cells. So the most common design for these kinds of power systems, like the one on the International Space Station, all feature this design where there's a photovoltaic cell, there's a very thick layer of glass. I showed you techniques on Tuesday for making extremely thin, lightweight solar cells. But the problem is I can make the solar cell as light as I want, and I still have to put 50 to 100 microns of glass in front of this solar cell, and I've lost all the weight advantage I had from making the solar cell thin. I have to also put a radiation shield on the back surface. And then the mass density gets to be so high that I can't get to more than a kilowatt per kilogram. I can't reach the objective that I was trying to get to. So I have to find some other way to solve this problem. So one, and this sort of illustrates it dramatically, the solar cell itself consists of a front contact, back contact in the cell, but I have to put shielding on top and the bottom, and the shielding represents, this is saying the same thing in this pie chart, most of the mass, and so that would limit the power density I could get to about 400 watts per kilogram. And our goal is to get to 1 to 20 kilowatts per kilogram. So therefore, we're going to go to concentration. And why would we do that? That's because what we can do now is, instead of putting a radiation shield over the entire surface of the photovoltaic, in a concentrator, I work with very small cells. The cells are millimeter wide strips. This is a trough concentrator, a one-dimensional concentrator, where the incident light is concentrated by this parabolic mirror onto the PV cells on the mirror in front. It's a multifunctional design. By the way, this acts as a structural support, a thermal conductor, a radiation shield, and a thermal radiation management system for the whole module. So it's fairly highly engineered. And this structure of the mirror consists of a number of optical coatings that are used to emit efficiently into the cold background of space and to reflect visible light efficiently onto the photovoltaic. So this is, and I showed you the tile, and the tile consists, and these structures have a mass density of 220 grams per square meter. It's a pretty lightweight structure. That's like about the same weight per unit area as a number 10 envelope or so, maybe with a letter inside. But that's about the mass density of the structure. These are carbon fiber reinforced structures, and that are molded, especially laid up and molded, so composites, and upon which we spread a polymer that capillary flow smooths out the surface to make an optical quality mirror. So actually, these are ultralight, high performance components made with space grade materials, all carbon fiber, and the only metal materials are a few hundred nanometer thick metal thin films. So, okay, even with this kind of structure, this is about the limit to what we can get to, and we're still stuck with this radiation shielding, and it turns out that this structure, I have to point it exactly at the sun, since it's a concentrator, and that limits the versatility of my spacecraft. So what I'm really interested in finding is a material that has very low mass per unit area, but wouldn't have the complications of the materials sensitivity to radiation that gallium arsenide has. So one of the materials that has been leading the worldwide research community on an incredibly energetic development cycle over the last 5 years are the so-called organo-lead halide perovskites. This is not an oxide perovskite that is familiar to many of you. It is a perovskite. It's a perovskite crystal structure, but one which has halogens like iodine on the rather than oxygen on the perovskite octahedral and it has typically organic cations, and then uses something like lead as the center B atom in the AbO3 crystal structure. These materials are remarkable photovoltaic materials. They are seemingly immune to defects. In polycrystalline films, they have performance that rivals that in terms of the luminescence and the voltage performance. The gallium arsenide, I showed that in some of the slides on Tuesday. They are very highly absorbing. You can spin coat them as thin films. You can doctor blade them. You can spray coat them onto polymers. And the thing that's remarkable is by putting them onto a polymer substrate, it's already been demonstrated that you could have a power density of 20 kilowatts per kilogram. So one of the downsides, and the reason they haven't sort of overtaken the terrestrial PV business, is that they are moisture sensitive. Now in space, of course, there's no water. On Earth, there's plenty of water, and so that's the thing that's holding them back. And much of the research in this field in photovoltaics is focused on how to solve the environmental durability problems related to moisture uptake. There are dissociation reactions for the perovskite molecular structure that are fundamentally decompose in the presence of water. And the limiting efficiencies for these materials are very high. So we decided to look at the space weather conditions for thin film perovskite solar cells. So we made a variety of thin film perovskite solar cells. These aren't particularly efficient. We've made other cells with efficiencies as high as 20%. They're not as high as the gallium arsenide cells, but the specific power, the weight per, or power per unit weight, is quite remarkable. Moreover, as we irradiate with electrons, this is done at the radiation facility Dynamitron at JPL, here's the gallium arsenide data. We're losing half the performance. Here's the perovskite data, completely unchanged in its power. This is without any radiation shield. So that implies that I could potentially, at least in terms of the electron performance, operate this with no radiation shield. Here is with proton irradiation. And this story's plot thickens a little bit. Same kind of cell here. It's a absorber layer. We have electron and hole transport layers here, nickel oxide for hole and PCBM for electrons, and then we have a transparent substrate here that this has been made on. So upon proton irradiation, we find that the solar cell voltage stays exactly the same. The short circuit current density stays exactly the same, but the fill factor changes. That seemingly suggests that there's some series resistance in the cell, in this absorber layer. We think it might be due to proton-induced deactivation of doping, or it may be that it is changing the properties of the interfaces here. Nonetheless, upon annealing at 90 degrees C, and by the way, every time a satellite goes from the dark side of the Earth to the bright side of the Earth, it goes from roughly 100 degrees C to minus 50 or 100 degrees C or so. So that you could think about a low Earth orbit as an anneal cycle. This solar cell recovers its performance completely. So this is a remarkable thing. So we're collecting now many gigabytes of data, not as many terabytes as Roger would hope us to collect, but we're collecting a lot of data. In fact, we look forward to working with his group on the data analytics. This is a remarkable statement. It says that this is a potentially radiation-hard, ultralight photovoltaic material. And so if we can simply encapsulate this in lightweight polymer materials, I think it's easily achievable that we can get into the maybe 20 to 25 kilowatts per kilogram specific power density. For reference, today's spacecraft are typically in the few hundred watts per kilogram range. Okay, so now I want to shift to my second topic to talk about space exploration and sort of what is the status of where we are today. The current status, if we look at here's a map of the solar system and a map of the solar system out to some nearby stars. Here's Alpha Centauri, for example. Notice that this is a log scale, and you can see here, this is the number of spacecraft that have made it to this distance, okay? That we have only 5 spacecraft that have ever been launched in all the space programs launched by all the countries around the world that have ever left the solar system. So, for example, here's Voyager moving at 17 kilometers a second past the heliopause out into the Oort cloud, the interstellar medium. But look how far we have to go. Here's the heliopause is here at a distance in AU of 100 AU, astronomical units or Earth units. Whereas to get to Alpha Cen, we have to get to 1,000,000 AU. So clearly we're going to have to go at a speed that is faster than this. So how are we going to do this? Okay, let's think about this, and the fundamental equation you need to know, and today you're going to all become aeronautical engineers, okay? So the most important equation to an aeronautical engineer is called the rocket equation, okay? And it expresses the velocity that we can achieve in terms of the exhaust velocity, in terms of the mass of the payload to the mass of the fuel. And this is a very, very sobering and discouraging equation. Notice that this ratio of masses appears in a log term. So for a chemical engine where we're using particles for propellant, the ejection velocity of the propellant is typically less than 5 kilometers per second. And the amount of mass to get to 10% of the light speed would be here 10 to the 4,500 times the mass of the payload. So this is just a laughable number. Even with an ion thruster, the kind of spacecraft like the Dawn spacecraft, we can get to higher, we can use electrostatic forces to eject the particles through electric fields at much higher velocities, but still we have just ridiculously large fuel to payload ratios. So the only fuel that's going to allow us to get there is light itself. And in this case, in the rocket equation, the mass of the payload and the mass of the fuel can be the same. And the final velocity of a recoiling photon here, instead of being 300 kilometers per second, is 300,000 kilometers per second. So that is what is going to make the difference for us. So we can say this another way, in terms of the time we would need to get to Alpha Centauri. So if we think about chemical rockets and we apply Newton's first law, and we take the fastest spacecraft that technology has ever provided, the New Horizons spacecraft, to get to Proxima Centauri would take 79,000 years. On the other hand, if we now use light as our propellant, as our working fluid, reflected from the surface of the spacecraft, it's reflected at the light speed, and so we impart a momentum 2 times the energy over the light speed. And now to get to 20% of the light speed, I'll show you at least a scheme by which we might be able to do this. We could get to Proxima Centauri in 21 years. And this concept was inspired by the many spacecraft that have already been developed over the last 20 years. In fact, there's quite a, in this year or next year, there's actually going to be quite a blossoming of technology on solar sails. This is inspired by the spacecraft that we already have that are propelled by radiation pressure. These are ultralight. These are typically these sails, like the JAXA solar sail. This is the only one that has really been used for interplanetary flight. These are basically demo objects. This one is basically about a 10 micron thick Kapton sheet that's aluminized with about 200 square meter area and has a small photovoltaic power conversion element in the center here. So this offers some mode of inspiration for this process. So let's think about this question more broadly. And this is actually was stimulated. This idea of going to stars is not only stimulated because of the technology that people are beginning to realize we may have some elements of. It's been stimulated by planetary scientists like my colleague Andy Howard and Michael Brown at Caltech and others, who have over the last 10 years, if you've been reading Science or Nature, you've seen that there's been an explosion in the number of planets that are being discovered. In fact, on Monday, NASA launched the TESS spacecraft, the Transiting Exoplanet Sky Survey Telescope. The idea is that it's a telescope that in space you point at a distant star, and as a planet transits in front of the star acts like a backlight that allows you to determine many properties of the planet, its size, its orbital period, its atmosphere, and tell you about the viability of this planet for life. And what the astronomers have found is that fully 1/4 of all the stars that they have cataloged have planets within the habitable zone. So habitable zone means that the temperature on that planet is close to 300 Kelvin, and that planet probably hosts an atmosphere. So that's a remarkable number. So if we think about the odds for detecting life outside our solar system, this is a pretty encouraging sign. So the question is, can we get there? Maybe. So what's our planetary neighborhood look like? If we look here where we are, then we can see the planetary neighborhood looks like this. This is a map in light years. We're here at the center. Alpha Centauri is about 4 light years away. Barnard's star is about 10 light years away. There are a number of stars here within 10 light years of the Earth. Okay, so that led this group of people. Maybe you recognize this gentleman who passed away recently, Stephen Hawking. This is Yuri Milner. Yuri Milner is an internet billionaire who has been an extremely successful entrepreneur who also has a PhD in physics, and he has founded the Millennium Breakthrough Prizes for basic fundamental science. And he is also the person that is underwriting a research program that has already begun and is actually going to begin, for those of you professors sitting in the front row, has issued RFPs for research, one on the laser system that I'll tell you about in a minute, and another on the light sail, which is coming very soon. So here's the concept. To use a laser that's based on the Earth, that has a wavelength, operating wavelength in the 1 to 1.5 micron range, that's based on the laser technology that's likely to be scalable, with a power of 100 gigawatts, optical power. So this is the largest laser system that would have ever been built by humanity. Aperture size in the range of a few hundred square meters to a kilometer. So this is nothing like this has ever been built before, but there's no law of nature or technology that stands in the way. The second is a light sail, and the concept is then to be propelled by radiation pressure over a time of 20 years at 20% of the light speed, with a spacecraft that has a weight of about 1 gram. The light sail has a weight of about 1 gram, payload roughly the same as the spacecraft itself. Okay, so let's see what this whole system might look like, and this is an impressionistic video from Breakthrough. This is a phased array laser. It's probably not the way it would really look. And this is the light sail, at least some artist version of the light sail, launched in low Earth orbit. And a phased array laser that, using individual lasers that are power combined, trains its large aperture focus onto the light sail and propels it from an initial height of about 60 million kilometers out to about the Mars orbit with CW laser radiation at a power density of a megawatt per square centimeter, or 10 gigawatts per square meter, over a distance of 4.3 light years from Earth to Proxima Centauri. So it needs to fly, let me turn the lights down a little bit, through interstellar medium. The Oort cloud is the interstellar medium, and we're now going through the interstellar medium. The sail would, if we could, we'd like to orient it end on so it wouldn't impinge on particles in the interstellar medium. We have a lower physical cross section, and may be able to communicate during its trajectory and navigate somewhat. And now it's passing Alpha Centauri, and on its way to Proxima Centauri. So Alpha Centauri is a bright star. Proxima Centauri is an M dwarf star. It's a small star that's smaller than the sun. And then it passes around a planet, or passes by a planet in the Proxima Centauri system called Proxima b, and flies by, takes pictures, and beams them back to the Earth using a laser communication system coming back to the Earth. So that's the concept that is envisioned by this point design that I've described to you. Let's see, I think that's basically it. Okay, so what do we need to do that? What we need are 3 elements. We need the photon engine, that's this large area, large aperture laser, phased array laser. And one of the things that makes this intriguing to almost everybody that thinks about it is that all of the individual elements at the basic unit element already exist. This would use solid-state kilowatt pump diode lasers. These are used by laser cutting and welding facilities already, kilowatt lasers. A light sail, and a star chip. The star chip, versions of this star chip have already been built. It's basically nothing more than the inner workings of your cell phone minus the battery and the display and so forth. Integrated circuit, camera chip, and so forth. The light sail needs to be lightweight, weighs about a gram, has an area of a few square meters, and therefore has a thickness for most materials in the range of a few tens to a few hundred nanometers. Okay, what about the photon? I'm just going to say briefly about the photon engine. The photon engine, we imagine, would be a ground-based laser system. The best place to put such things are on dry mountaintops, like the Atacama Desert in Chile, which is where many of the world's telescopes. This is the large European telescope located in the Atacama Desert. In fact, there are some places so dry here it hasn't rained since the Spaniards discovered this region in South America. So that's important because that makes the atmosphere highly transmissive for the laser. And you'll notice here in the 1 to 1.5 micron region, there's a pretty good transmission window through the atmosphere. Obviously, there will be scattering and refractive index distortion. And in order to compensate for that, this has already been demonstrated, the Air Force, one puts a beacon in orbit that takes off a portion of the light beam and uses it as a reference to determine the refractive index effects of the atmosphere. So the star chip, as I mentioned, really is nothing more that takes advantage of image sensor and integrated circuit technology and being able to make these in thin film form, which we can already do. In fact, several of the members of the Starshot team have already developed prototype chips of this kind. One can hope to and want to include many more sophisticated instruments into these chips that can do measurements beyond taking pictures or perhaps spectra. So I want to concentrate most of my remarks in talking about the light sail itself, because this is where a lot of the materials science and engineering lies. And so this essentially tells you what is the velocity that we can get to. This dotted line represents the velocity of the Voyager spacecraft. And this is the point design here, 20% of the light speed we're trying to get to. So what are the challenges? To have efficient momentum transfer, maintain the shape of the sail, to have it ride the beam stably and passively with a controllable trajectory and good stability. The material itself, of course, is being heated at steady state at a megawatt per square centimeter. So absorption is very important, as are mechanical stresses. And then, of course, we have to figure out a way to make such meter square objects that would and deploy them in space. Okay, so this is the basic equation that we need to use to understand what the sort of material selection requirements are. The final speed I can get to is based on the power times the array size divided by the wavelength to the 1/2 power times mass to the -1/4 over mass to the 1/4. So as an example, if I were to point this laser pointer that I'm pointing at the screen at an ant that weighs 1 gram for a week, I could get that ant to move at a millimeter per second by radiation pressure, assuming no other forces in the problem. So I'm going to have more laser power than that. That's why I need a very high power, maybe 50 to 100 gigawatts to get to 0.2 C to accelerate 1 gram in 10 minutes using a laser with a wavelength of 1 micron, a sail area of 4 meters by 4 meters that produces a diffraction limited beam spot size at a size of 2 million kilometers. And this idea, by the way, was already thought about by this fellow Bob Forward in 1962, 18 months after the invention of the laser. So Ted Maiman here at Hughes Research Lab in Malibu invented the Ruby laser at the same time that Charles Townes invented the laser in Berkeley. And Forward, who was one of the lab mates of Maiman, already thought about ways to use lasers for radiation pressure propulsion. And this drawing encoded in his 1962 paper was sort of a crude version of what we're thinking about today. So what are the issues for the materials challenges? We have a mass of a gram, area, call it 10 square meters, acceleration time of 1,000 seconds. We need to have very, very low absorption coefficient, otherwise the material will burn up. We have to have an absorption coefficient of 10 to the minus 5. We'll explain why that is important. We need to have reflectance that's relatively high over a broad spectral range. And the reason is, as we go from rest to 0.2 C, there's a Doppler shift such that the laser as apparent frequency is Doppler shifted by about 20% of the wavelength when it's at rest. So let's think about some of the materials candidates, the photonic design, some of the thermal and mechanical issues. I won't go too much into the fabrication, but we'll talk a little bit about measurement and characterization. So this is our sort of picture, and there will be a paper available hopefully later this month or early next month about this that describes some of this sort of material selection exercise I'm telling you about today. And in thinking about materials, we want materials that have very, very low absorption coefficient, and this is absorption expressed in inverse centimeters, mass density, which of course is as low as possible in grams per cubic centimeter, and high refractive index, because it's easier to make dielectric optics and highly reflective materials with high refractive index. So these are materials that pop out as interesting materials. So crystalline silicon is a good material. Diamond is a good material. Some of the chalcogenides, tin sulfide, molybdenum disulfide, molybdenum diselenide, may be all interesting materials to use. So the Doppler shift, of course, if you think just about special relativity, the observed frequency by the laser, which is sitting on the Earth, is changing as the sail accelerates and changes its velocity. And so it's going to shift by about 20%, and the laser frequency will go down about 80% of its frequency so the laser light will appear redshifted to the sail. So I'm going to say a little bit about how to do design, and this is sort of a design exercise that's determined by a multivariate constraint optimization problem. And we're interested in sort of exacting a trade-off between many different properties of this sail and identifying candidate structures. And so our approach is to use a multivariate design optimization across different classes of nanophotonic structures. I'll show them to you in a minute. And the design exercise involved a total of more than 100,000 electromagnetic simulations of the electromagnetic modes and fields. So these are the structures that we're going to look at. We're going to look at dielectric slabs, just a uniform thickness, homogeneous dielectric slab, just a sheet of material. A multi-layer stack. So imagine you had high index sheets with low index sheets of a material like aerogel between them, and up to maybe 7 layers. So-called 2D photonic crystal. This is a motif that's familiar to optoelectronics people. We can make structures that exhibit guided modes and band gaps within the plane using a film that has a periodic array of holes. This gives rise to block-like modes for light, periodic modes for light inside the film. And this is a structure that I talked to you about yesterday with arrays of antennas, in this case not metallic, because we need low absorption. These are dielectric antennas. And we've permuted all of these variables, the thickness, the number of layers, the period of these structures, their radius, and their height, with a variety of different materials, silicon, diamond, and these 2 metal chalcogenides. So for each of them, we would like to optimize them relative to some figure of merit. And the question is, what should that figure of merit be? So we started with thinking about what are the figure of merit, and we have many different points where we seeded the algorithm. And we decided there are a couple possible figures of merit. First would be just make the reflectance as high as possible. That seems fairly intuitively reasonable. So you have more momentum, and if the reflectance is very high, you could perhaps mitigate the absorption. Or you could use as your figure of merit to make the acceleration distance to reach the final velocity be as short as possible. And that's really what you care about, because that doesn't that's really just telling you you're minimizing the energy cost required, because that's the time that the laser has to be on. So it's directly related to the required size, cost, and of the phased array laser, which is the most expensive part of the system. So this is sort of in the Ashby spirit of material selection. We're going to design for a system application the performance characteristics of the material that minimizes or advances some specific goal, in this case related to this very costly element. So the acceleration distance is now related to the speed of light, the area of the sail, the reflectivity, this relativistic correction, velocity, and so forth. And so I can compute this distance that I need to, so for those structures that I showed you, we permuted over and made a little more than 100,000 different simulations. And here's what we found. We found an array of solutions where the reflectance was close to 100%. And the good news is that for the two candidate materials we analyzed in detail, molybdenum disulfide, multi-layer molybdenum disulfide, like the materials I showed you we made solar cells of on Tuesday, or thin films of crystalline silicon, there are many solutions. I have photonic crystals, I have slabs, I have stacks of materials that all work. But you can actually do even better, and this is somewhat counterintuitive, by relaxing the demand on having the reflectance be close to 100%, and say, and notice this is an inverse scale. Large distance for acceleration is on the bottom, short distance is on the top here. And so this is the optimal solution. In this case, it's a photonic crystal that looks like this. And the reason is very simple. By putting holes in the photonic crystal, we take away some of the weight. And so it turns out we can give up a lot of reflectance in our design optimization in favor of getting rid of the weight. And so that has a reflectivity, can reach 0.2 C according to this analysis in even less than 1,000 seconds. And this actually, surprisingly, you would have thought perhaps the optimal one would have a reflectivity of 99.9% across this whole band. This is the reflectivity of the optimal structure. By giving up the weight, we were able to the optimal solution told us we could sacrifice. So this tells you that multivariate optimization and learning can lead you in counterintuitive or non-intuitive directions. That this is the reflectance profile. It's actually not very reflecting at all until it gets up to here. It's not even 100% here, and it goes down. And this is the entire bandwidth over which the sail experiences the light as it accelerates. Okay, what about the actual physical characteristics from an optical sense of the materials? All the materials we're talking about are dielectric materials. They have wide energy gaps. Therefore, they have absorption at short wavelengths. They have coupling between the optical phonons and the lattice at long wavelengths, the so-called Ristron band or phonon-polariton modes. They also have defects that give rise to color centers, that give the crystals physical color due to trap-to-band transitions. So these are the generic characteristics of these materials. So what we need is to have materials that have very, very low absorption coefficient. So this is the absorption coefficient in inverse centimeters of materials that we found data for: molybdenum disulfide, amorphous silicon, crystalline silicon, or diamond, and here crystalline silicon. And then we also need to have, it's important, we need to have very low absorption at the pump laser wavelength, right about here. But we also can't have lossless material here because we have to have some emissivity. I talked about the balance between absorption and emission yesterday. We have to have a material that has finite emittance. So we need to have some emittance, some absorption here at long wavelengths outside the pump laser wavelength band, such that we can use blackbody radiation to cool the sail. That turns out to be very important. So I won't go into this in detail. We have methods that were developed first at Lawrence Berkeley Labs and used actually to characterize the mirrors for the LIGO Michelson interferometer, called photothermal deflection and photoacoustic spectroscopy. They basically measure a temperature-induced refractive index, and they can make measurements of refractive index that are a couple of orders of magnitude more sensitive than we can by ellipsometry or conventional transmission measurements. And so these measurements have been made for diamond and silicon. These measurements are pretty old. That tells me they may not be wrong, but they may not, we might be able to improve upon the materials performance and also the measurement sensitivity of these instruments. So I think there's going to be a need for new measurement science to address ultra-low absorption coefficients. So this is what some of these apparatus looks like. I won't go into this in a lot of detail. The photothermal deflection invented by this guy Warren Jackson, and he later went to Xerox PARC. So thermal management. I mentioned in order to do thermal management, I have to have some emissivity. And so, for example, in the case where I have a light sail that is made out of a dielectric material that contains, that has phonon polaritons in the 10 micron or 10 to 20 micron range, I have now some absorption and therefore some emission of light and radiation at this wavelength. And so what we found was that by making laminates, say, of a highly reflective material at pump wavelength like silicon, and silicon dioxide, which is transparent at the pump wavelength, but which has these phonon polariton or Ristron bands. This, in fact, is the refractive index and absorption for silicon dioxide around 10 microns. Many of you may know, if you've ever shined a long wavelength laser, silicon dioxide, which is transparent and the visible, is opaque at 10 microns. So this allows the appropriate balance, and even with emissivities in the range of 10 to the minus 3 or 10 to the minus 4, we could keep the temperature of the sail to maybe 500 to 700 Kelvin. So a couple hundred degrees C, which is probably acceptable within the range of things we're interested in. What about mechanical properties? Well, I look for your feedback, but here's what we've thought about, which is, first of all, most of these materials are basically ceramic or brittle materials, so they have incredibly high compressive stresses. You have to worry about shear, but just the hydrostatic compression, there's really no issue. They have high moduli, but they're delicate in tension. So what about the tensile stresses? So we decided to make an analysis, say, assume we had a structure the size of a light sail that was, say, a disk or a sphere. What rotational speed could it get to before the material at the edge of the sail exceeded the tensile yield stress of the material? And so here's some typical tensile yield stresses for boron nitride, silicon nitride, aluminum nitride, amorphous silicon, and so forth, in the range of 10 to the 8 to 10 to the 11 pascals. And so that basically tells you I could tolerate rotation of the sail up to, for the diameters we're talking about, a few square meters, up to a few tens of hertz or so. You wouldn't want it to rotate faster than that for fear that you would compromise the tensile strength. At least that's my picture of this. So what about the stability of the sail itself? It's a dielectric passive object. It's moving so fast I can't do feedback control of the communication. It just has to ride on the sail, just like optical tweezers traps a little bead, or like these fountains of air can suspend a ping pong ball. It has to be passively stable and to have basically a little potential well, an optically induced potential well. So we want to design the optical properties of this so that we have such a potential well. So we can write down basically a force equation, and in fact this is a sort of 6-axis model where we can look at the displacements and forces in x, y, z and r, theta, phi. And it's dependent on the beam profile, the reflectivity, the angle of incidence, the absorption, and the beam propagation. So this is the governing equation. I won't go through it in detail, but it's a rather simple governing equation that captures most of the important dynamics. So here's an analysis. This was done by Avi Loeb, my friend as an astronomer at Harvard, Zach Manchester, who's a mechanical engineer at Stanford. By the way, this tells you something about this field. It's bringing together astronomers and mechanical engineers. And they did an analysis of what would happen if you had a donut-shaped beam and you had a spherical dielectric sail with forces acting on it. And if you have some unbalancing of this donut-shaped potential, you could start to induce rotations. So the sphere is stable as long as it doesn't rotate. That's good. The stresses are compressive. That's good mechanically. And then some of the other things that you worry about are what happens when the sail tips off axis? Is it going to wander away from the beam? What happens when the radiation pressure deforms the sail? Does the net force still give it the right velocity? And how does the mass distribution affect the problem? And so what we're going to do is actually look at some unconventional optical designs. So for example, one thing you can do is to make the sail be here a parabolic shape, a paraboloid. And even if I choose a paraboloid with a safe radius of curvature, not too sharp, not a cone, cones are unstable, a Gaussian beam, it can be stably coupled to this structure. I can write down all the equations of motion. I can linearize them. In fact, I can keep the full non-linear solutions. And I have stable solutions. We've done this. And I'll just show you what they look like. This is an example of a paraboloid. And this z-axis whizzing by is a scale. It's traveling here at meters per second. And you can see relative to the initial, let me start this again. Yeah, it starts out and it has some axisymmetric instability, but it settles down and it has a stable, and it exhibits stable oscillatory motion around the center point of the laser beam. So it actually has an attractor basin for the solution of the trajectories as long as you have a certain Gaussian beam shape and radius of curvature. So now what I talked about yesterday was the idea of patterning the surface and making metasurfaces. So I can change the dispersion of light. Here's an example making a lens and I talked about antenna arrays yesterday. So instead of just using the specular reflection from the bulk optics, I could use the dispersion or the angular distribution of light to stabilize the sail. And here's an example of the trajectory. And this shows the trajectory of a sail that first moves off axis, but the angular distribution of the scattered radiation steers it back on axis and back on axis and so forth, so it stably oscillates around the center trajectory. So now we can combine the photonic design here with the shape of the sail. In fact, this is for a disk, so it's completely flat. And you can see just by making this photonic angular dispersion be controlled, I can apparently make stable solutions. So, okay, I talked about some pretty fantastic numbers. 100 gigawatts, a laser so big no one's ever built it. Kilometer size, 10 meter square structure, it's 100 nanometers thick. Sounds pretty spectacular, maybe a little imaginary. Let's think about what we could do using materials that we already have today. So for example, at many places and a number of laboratories around the world, we have lasers with power already available in the 100 kilowatt to 10 megawatt range. So if we had a sail that was less than 10 square meters, say was only now 10 centimeters or a centimeter in size, I could still, even with 100 kilowatt to 10 megawatt power with available lasers, achieve velocities that are higher than the velocity of the Voyager spacecraft by a factor of 10. Alrighty, so with the things we have available today, we could be launching structures that move 10 times faster than some of our fastest spacecraft. So I think we don't have to go all the way up here before we start doing things that are exciting and interesting from an engineering point of view. Okay, so what is the sort of vision here? Scalable space exploration with photon propulsion. So we can get across this map, maybe launching spacecraft ultimately to our nearby stars. But for example, if we could go to 20% of the light speed, the travel time to Enceladus, the moon of Saturn that's expected to have an Earth-like ocean, which has an Earth-like ocean, would be 5 hours. If you're a graduate student, you could launch the spacecraft and the next morning you'd have the data. Rather than in Cassini, where the spacecraft took 12 years to go that same distance. So I think it could really revolutionize planetary exploration and exploration of our solar system. Okay, so I want to, just before I quit, once again acknowledge the fantastic young people who have been involved in this project. This is a group, we started out with no funding for this. In fact, we have some discretionary funding. This was simply so irresistible to this group of people that they spent their Saturdays and Sundays meeting with me, going over and doing some of the preliminary engineering and materials design. I'll point out Deep Jarwal is now at University of Pennsylvania, Michelle is at MIT, and Mike Kelsenberg is a staff member at Caltech, and the rest of these are graduate students and postdocs in our group, and they are the people that really make this all possible. So thanks very much.
Questions? Okay, I saw Will, I think I saw your hand first.
I was wondering if it was possible or considered to induce a gyroscopic effect to stabilize it. If that would be
So within the limits of the, and I'm looking here for some of the mechanics people to correct me, I think the issue is just the tensile yield stress of the material. So I think it would help, but actually the analysis, the stability analysis that I talked about didn't require any angular momentum. In fact, we're thinking that maybe we could actually make the laser sail be polarization sensitive, so that some linear polarized laser beam could actually lock in the orientation of the sail, and maybe you could then rotate it at you could rotate the polarization, which you can do electronically with a power combining laser beam, a synthetic beam, and rotate it at whatever frequency you want to actively. Yeah.
In materials, what about graphene? The least heavy and also.
So that's the question I am most often asked. Why not? What about graphene? Graphene did not show up on my slides. The problem, and I love graphene. I work with graphene. Graphene will never work at the high power densities needed because the absorption coefficient is too high. So it really, the key insight that came out of this analysis was I expected that many materials would be possible, and that if we just made the reflectivity 99.999%, that doesn't matter. What matters is that the absorbance be very, very low at the wavelength. So graphene, unfortunately, loses out. This has already been proposed by other researchers, and unfortunately, I don't think it's viable. Yeah.
Back to the halide perovskite
Yes.
solar absorber materials. Is there any mechanistic understanding as to why they are so radiation resistant? And if I understood you correctly, they can recover
Yes. Yes.
darkness.
There is.
Form defects or?
Yeah. So the thing that's remarkable about these materials, I didn't dive into this, and I could certainly do so. They are almost liquid-like at room temperature. They have mean atomic displacements of like 15 to 20% at room temperature, which is almost the melting criterion, right? So these are materials that are very unusual. They're not. They have very soft phonons. So they're very unusual, and that is one of the reasons why we think they don't have deep electronic states in the middle of the band gap, which is why they're such good solar materials. So they're almost liquid-like, and their bond rearrangements locally are very facile.
That sounds fascinating.
Yeah.
Al, and then John, and then...
It's related to that. So these perovskites, they are not cubic from what I saw. They have domain walls, etc. And in piezoelectrics, we use radiation hardening sometimes to stabilize domain walls. How much does that kind of presence of domain walls affect this radiation?
I don't know the answer to that question. I don't think they are piezoelectric in the state that is used in photovoltaics, but
still.
By the way, one thing I should also mention is that in some of the perovskite materials, there's also ion transport as well. There's ion rearrangements in the lattice. It's they're very there's a great deal of atomic motion at the unit cell level in the material.
Extrusive titanate is not piezoelectric, but at low temperatures, for example.
Yeah, so that's why I'm hesitating, because I don't know the answer whether at lower temperatures it might be. I suspect you might be able to see a phase transformation. Yeah.
Harry, you showed like in your search for the optimum material and structure, obviously there's different things you want to try to maximize or minimize, and you showed that in addition to the material, you could make a structure with pores in it.
Yeah.
Of some amount and size. Could you describe a little bit more about how you've done that already? How did you put them in a regular array?
Yeah, so those are made fairly routinely by practitioners of making photonic crystals. You can make them in a clean room or by a printing process, an etching process. You can make holes in a thin film, and we make 2D photonic crystals. In fact, many waveguides and lasers and so forth depend on these arrays of holes.
Very conventional.
Pretty conventional, yeah, actually. So that was not. So I should say that the consequences of doing that for the mechanical properties haven't been analyzed. So whether that's going to end up, and that's an important. There's a lot of work to do here. I don't in any way. This is very much the beginning rather than the end of the story.
And the sizes of those were roughly what?
So they're in the range of a few hundreds of nanometers, something like that. So they're relatively small. They're wavelength scale within the silicon. So yeah.
So I don't know if you're finished answering the previous question, but okay, back to the perovskites. It's so surprising to me to find out that ultimately their benefit is in sort of their efficiency per weight, because they have all heavy atoms in it, like iodine. So is it ultimately because you can make them so thin because they're so fantastically absorbed?
Yeah, they're very high absorption coefficients, and yeah, that's right. And in fact, the other feature about the way radiation interacts with the materials is that they're so thin that all the protons and electrons go straight through the material. So if you think about how energetic particles lose their energy in materials, for heavy particles like protons or heavy atoms, the displacement defects are always produced near the end of range when they come almost to rest. And while the particle is going swiftly through a material, it generates electronic excitations. So I think that may be part of it, is that all the damaging particles the layer's so thin they just go straight on through, and so you have electronic excitations. There is some, there's some electronic effects. We see what an apparent dopant deactivation, which you don't fully understand and trying to understand, but no irreversible damage. Yeah.
One thing I think they are a little bit on a bad news is I think they're not only unstable in moist air and in moisture, but they're also, I think, somewhat unstable under the influence of UV light itself. And there are other crystal structures that are competing that some of us theorists calculating, I think, are even actually the ultimate stable form of these materials. So
yeah, the story is still being very much written. Yeah, yeah. So I didn't give much backstory, but there are literally thousands of researchers around the world, for those who are not in this field, who are working on looking at properties of the perovskite materials, and that's true. And recent data suggests that there are versions of the material that have less and less residual solute or solvent, that are more stable, have less unwanted ionic transport during the cell operation, that make the material more stable under ultraviolet radiation. But it's a complex story with many nuances. Yeah.
Okay, I'm scanning the room for student questions, so I'll do Je and then you, Dave.
I have a question. As the laser, the power laser is pretty large, and so I'm considering during the propelling process with the laser would either lead to the temperature rising of the whole vehicle or even damage it.
So, temperature rise of what?
Of the
sail?
Of the sail?
Yeah, sail.
Okay, that's why the absorption coefficient has to be very, very low. If the material is not absorbing at the pump wavelength, then the temperature rise, even these power densities, can be, that's what these calculations. So of course we have to verify this experimentally. We're actually building experimental systems to do this right now. But the suggestions are that if we can get the absorption down to 10 to the minus 5 or lower, that the temperature, so little laser power will be absorbed that the blackbody radiation to the cold background of space can maintain the temperature of the sail in steady state at hundreds of Kelvin, or a few hundred degrees C or so.
Ideally, you want a mirror.
Ideally, you'd like a mirror, yeah. But the reality is that in all mirrors, some of the light penetrates in as it comes back out. So that's why you need a lossless mirror, yeah. Yeah.
And the whole purpose of the sail is just as a surface to be pushed.
That's right, yeah. So that's its function, yeah.
So I was struggling with the orbital mechanics of having your laser array fixed on planet Earth, which is rotating and wobbling and orbiting the sun and trying to hit this object far away. It seems to me that in your force balance, this is going to be an impulse. It's not a steady beam that's going to encounter it, but there will be interruptions to the beam. And so the interaction with the sail is going to be an on-off.
I'm not quite sure I'm following.
So you're on the Earth,
yes.
And you're fixed, and your beam is fixed.
Yes.
And the Earth is rotating.
Yes.
But your object is out here. So there must be some
okay.
angles at which your beam is not going to be able to hit that.
Oh yeah, okay. So the entire duration of the impulse is about 1,000 seconds.
Yeah.
And so the phased array can steer the beam to maintain its Gaussian beam focus on the sail during that time. In 1,000 seconds, the Earth is rotating, but the steering can compensate because I can steer a phased array beam.
But from the material aspect, then your momentum, you have a beam of momentum that you're pushing the sail, is going to be an on-off. And I'm wondering in your dynamic forces, if you've looked at that.
Maybe we should talk about this later. I don't quite see the on-off nature of it, but okay, yeah.
And so I'm going to take our last question because tonight Professor Atwater is going to be driving to Dayton, so we want to make sure he gets dinner and can head out. So,
So you were talking about, this goes really touch several space and, to have this low angle or so, and that was with the sail. Is there a use for that sail after its initial acceleration, or can it just dispatch and just...
That is a subject of debate among people in the project. Some people say its job is done. Other people would like to use this sail as an antenna for the communications aperture to beam information back. And the question of whether that's a viable scheme will probably depend on the damage it experiences in the interstellar medium. If you go to astronomy journals or consult your favorite astronomer, they can only bracket the density of the interstellar medium now within about 2.5 orders of magnitude. So there are some things we still don't know about the universe. So.
Okay, well, I would like to thank Professor Atwater one more time and bring the 2018 Van Horn Distinguished Lectureship to a close.